One of the main important features of a radioactive element is its half-life, and what this means is the time it takes for half of that substance to decay into something else. So earlier we talked about carbon-14 decay. Its half-life is 5,700 years. You might see it written like this, a T with a little 1/2 subscript. What this means is if we were to create a kilogram of that today, and we waited 5,700 years, half of it would have turned into something else, nitrogen or some other product, if that nitrogen is not stable. You wait another 5,700 years, so now we're at 10,400. Now we're down to half of it left, or 1/4 of it. And this is statistical, so it works great when we have a large number of atoms, just like for a given roll of a six-sided die, we can say you got a 1 in 6 chance of getting a 5. Now, let's say you take that die and roll it 6 times. What are the odds that each number pops up exactly once? You don't really expect that to work out, and it doesn't mean you somehow have a bad set of dice or something. Now, if you rolled the die 600 times, you'd probably get each number to pop up around 100 times, maybe 98, 97. You did it 6 million times, your numbers would be very close to a million for each. So what this means is we've got a really good idea of how long it takes half a kilogram of our kilogram to decay. But once we get down to 2 atoms, we have no idea when either one will decay. They might both go immediately, they might wait 20,000 years. And this is not the way things work in biology. A 30-year-old and a 95-year-old don't have the same life expectancy. But our brand new atom of carbon 14 is just as likely to decay if we watch it for a day as a 10,000-year-old carbon 14 atom. Now, this isn't usually a problem because we generally work with a ridiculous number of atoms, but you should know it's a statistical thing. Because it's random, it turns out that the rate of decay is an exponential function. So if we start with some amount of material that we call N0, the amount we have after time t later is, N here as a function of t, is N0 e to the negative lambda t. This lambda is the decay constant, and it's different for every element, every isotope. And we can connect it to what the half-life is because they're both telling us the same thing, only in different forms. So what we can do is say, well, all right, how long until n of t is 1/2 of N0? We put in the numbers here, and we do some algebra. We can write 1/2 is e to the negative lambda t. To undo e, we have to take the natural log of both sides. So natural log of 1/2 is negative lambda t. We know t has to be the half-life, so we can write it like that. We can say log of 1/2 is negative lambda t half-life. We ask the calculator what the natural log of 1/2 is and get this. So finally, we can say the decay constant is 0.693 divided by the half-life. Now, the reason carbon-14 gets mentioned so often is because it's the kind of carbon that you collect from the air while you're alive and breathing, and this includes plants. Once things die, they're not breathing in any more carbon-14, so we know that it's going to decay from there, and we'll be able to figure out how long ago something died. This works pretty well for up to 10 half-lives, roughly. If you do the math, you'll see at that point you're down to about 1/1000th of your original material. That would mean about 50, 60,000 years. So the experimental uncertainties start to get big. We start to end up with those small number problems like we talked about with the dice. We can't get ages of rocks with carbon-14, even if they breathed, because their ages are billions of years. And we're going to have something with a longer half-life. And one commonly used thing, if we look at uranium, there's really only 2 natural isotopes. Uranium-235, which is what they build atomic weapons out of and put in nuclear reactors, and uranium-238, which is sort of the boring stuff, although it has been used in anti-tank weapons. It's called depleted uranium. The half-lives of these things are about 700 million years for U-235 and more like 4.5 billion years for 238. So if you look at what fraction a given rock has of each of these things, you've got a pretty good idea of how old that rock is. That's how we know how old is the moon, how old is the Earth. That gives us a good idea.